processing and computer vision, what is automated optical inspection, how we can use machine learning to build our anomaly detection models, and how image processing can help improve the accuracy of those models, and finally, how we can integrate those analytics into other systems. So image processing and computer vision are strongly related and are often used interchangeably, but they are different, right? So image processing mainly deals with how to manipulate the pixel information in an image or a video. And it often deals with how we can enhance the properties or features of an image so that we can get it ready to train another machine learning model or some other information extraction tool. Hence, we speak of techniques such as contrast adjustment and things like edge detection. In contrast, computer vision has to do with how we extract information from a real world scene. So this has to do with how do we interpret that image. And hence we speak of things such as detection, classification, and tracking. So these are just some examples of different applications of computer vision. So in the top left corner, we have computer vision for human detection. And this often has to do with tracking the movement of people within a particular area. So if we start thinking of a mining site or even a manufacturing site, you might not want your employees to access certain regions because of safety reasons, or because of now in these COVID times, maybe you want to ensure that people are following social distancing protocols, right? And then on the right, we have computer vision for semantic segmentation on multispectral satellite images. So this is often useful if we want to extract information about the abundance of a particular element in an area. So think of finding how many trees are in a particular area, or what are the number of routes or roads available in that area. And you can use computer vision to detect defects in your products. So if we think of a production line where they're probably producing thousands of products per day, you want to process or analyze the quality of those products as efficiently as possible. And we want to consider how can we automate that process. And then lastly, we see here that they've used computer vision to detect people wearing masks, right? And this is something that has become valuable because of these COVID times. But if we think on the context of manufacturing or mining industry, then we think of maybe detecting if people are wearing their PPE. So are they wearing their helmet, their eye protection gears, or their overalls and boots and all the right equipment so that they can work safely? So as part of this webinar, we will focus on how we can apply computer vision for defect detection. So let's start by first defining what do we mean by automated inspection, right? So it is automating the process of visually inspecting manufacturing parts for defects and failures. So this is where we consider a failure as a consequence of a quality defect that results in incorrect behavior of the system. And there are various terms that you may have heard being used to describe this process, one being automated defect detection, computer vision, machine vision, visual inspection, and automated inspection. So let's look at a practical example. So here we have a very real client called Nuts and Bolts Manufacturers who naturally produce nuts and bolts. And in this webinar, we will go through some of the technical details behind how this very real company implemented and integrated automated optical inspection into their production lines. So Nuts and Bolts has a team of product specialists who essentially sit and visually inspect the quality of each bolt every day. Now, if I present you with 4 bolts to inspect and I ask you to identify those which are defective or faulty, then that's not a very difficult task because it's very easy to see right away which one is defective. But what happens when I present you with more images? So in this case, we are looking at 15 images, identify which ones are defective, and it gets a little bit harder because you have to concentrate a little bit more, right? And the reality is in the manufacturing business, you're probably producing hundreds to thousands of products at a time. So you might not be dealing with just a case like this, but something as bad as this. And I can go on, but I think you get the point. And obviously, as a nation, we are relying on Nuts and Bolts to supply us with A-level bolts and to meet our demands. So what does this mean for them? right? It means that they need to make sure that the inspection is both quick and accurate. So essentially what nuts and bolts needs is an efficient AI system that can help, automate this process. So if we start to think of the reality of this process, it's almost as if you would have these bolts sitting on a manufacturing belt. Then you would have a camera that captures that bolt, and then that image would then be processed and analyzed so a classification can be made in terms of, is it a good bolt or is it faulty? So now let's look at the specifics of this process. So the first thing we need to do is to access and explore our data. And that data can exist in .jpegs, PNGs, or .tiff files. And we need a platform that can support that variation. The next thing is we want to pre-process that data, meaning we want to get that data into a format that is suitable for training a machine learning algorithm, right? And pre-processing entails doing some image processing that we spoke about earlier, where you want to enhance some of the features or properties of the image. It also entails the labeling and cleaning of the data, so that which is normal versus that which is abnormal. And once we have that data in the right form, we want to develop a predictive model from it so that we can perform that classification. And then finally, how can we integrate those analytics with other systems? So is it going to be a desktop application that members in your, staff members in your company have access to? Does this have to be an enterprise-wide application that members of your company at various levels of hierarchy have access to? Or is it something we want to deploy to some edge device so that people right on the ground have access to that type of technology? And throughout this webinar, we'll discuss various parts of this workflow and some of the challenges that are faced at each stage, and how we at Opti-Num use our experience with MATLAB to kind of address some of these challenges. So one of the most challenging things is deciding on and designing the predictive model. So for this problem, I'll consider a deep learning approach, so for performing the classification of good versus faulty. So when we consider a deep learning approach, there are typically two methods that we can follow. So the first is we train a neural network from scratch. That means we define the layers and parameters to refine its classification of whether the bolt is good or faulty. Or we can use a transfer learning approach, in which case we take a pre-trained neural network, we modify it slightly so that it can perform the task that we want it to perform. And regardless of the path you take, there are benefits and challenges to both. So in the first case, the benefit is you're almost guaranteed a higher accuracy on the image classification because you have built a neural network that caters to your specific problem, right? And in the second case, transfer learning is a lot easier to use because you would require a much smaller data set. So think a couple thousands of images instead of millions of images that would be required when training a neural network from scratch. And when it comes to the challenges of training a neural network from scratch, you would have to prepare your image data. Now imagine sitting all day labeling millions of images of that which is faulty versus that which is good. It's a lot of work, right? And for either case, the next challenge is the data set has to be balanced. And that means you want to have equal or close to equal quantities of data within each class. Because the moment you have more data in the one class, that bias then gets introduced into the neural network. And that means all your classifications would be in favor of the larger data set. So let's look at our task, right? So we have 4 defective units in 100 test images. And there are some challenges that are associated with it. So we have 200 images of bolts. And of those 200 images, we only have 4 that are defective. So we need to identify 4 defective units in 200 images. And this means that our data set is not balanced at all, right? And for some strange reasons, manufacturers aren't very keen on destroying their products for the sake of training a model. It's very difficult to work with them, but you know, what must happen? And this means it makes it very difficult for us to work with the approaches that I mentioned previously. So that means we have to think of a slightly different approach, right? So instead of thinking, okay, let's train this model to learn what normal looks like and what abnormal looks like, we'll just teach it what normal looks like. And because it'll have a very good idea what normal looks like, it'll be able to use that criteria to understand anything that doesn't fit into that criteria. And it will thus classify it as either being faulty or abnormal. And in this approach, we would still want to leverage the power of deep learning. And the reason for that is deep neural networks are very, very good at extracting features from data, even image data. So, for example, we would take an image still and we would pass it through specific layers of our neural net. So I'm just going to pull out my pointer. So in this case, we will use the first convolutional layer of our neural network, and that essentially contains a collection of filters, right? So you can think of a filter as a thing that would extract a particular feature from our image. And this is essentially a montage of all the features that have been extracted from this fault in particular. So if we think of, for example, this tile over here of information, we can see that it's doing a very good job at detecting the edges of the bolt, but it's activating quite strongly from when we're transitioning from light to dark. And in contrast, here we have this tile behaving similarly, where it's detecting edges where we're moving from dark to light. And the rest are all different features that have been extracted. And unfortunately, we might not find it easy to interpret what each feature is, but it's not our problem because the neural network has got it all under control. And then we'll use the seventh fully connected layer. So the seventh fully connected layer would essentially flatten that information. So getting it into a vector, and because that's the form needed by the machine learning algorithm to train from the data. And in this case, we'll be using a one-class support vector machine. And again, just remembering that our one-class support vector machine will essentially just look at and learn what normal looks like, actually be able to identify anomalies based on the fact that they are not similar to the rest. So let's move into MATLAB for a quick demonstration. All right. So the first thing we want to do is to load in our neural network. So for this problem, we will be using the Alex network. And the next thing we want to do is to visualize that neural network. And to do this, we will be using the Deep Network Designer. You can also access it by moving to your Apps tab, selecting the drop-down, and under the Machine Learning and Deep Learning section, you'll find it placed here, along with the various applications that are available. So the neural network that we'll be using is the AlexNet. So this is a neural network that was created or designed by a man named Alex, and it was essentially trained on millions of data, millions of images, and can classify into about 1,000 categories. I'm just waiting for my neural network to load. All right, so I'm just going to zoom in so you can see the details of the neural net. So you can think of each block in this interface as a different layer of our neural network. And each layer is responsible for performing some sort of manipulation to our input image. And I mentioned that we will be using the first convolutional layer. And the first convolutional layer is responsible for extracting those features from our image. And we see here, we get information about the properties of that layer, and it tells us that it has 96 filters. So that means from one image, we will be extracting 96 properties or features about that image. Right? And then the next thing we want to extract is our seventh fully connected layer, which is over here, which again is responsible for flattening the information into vectors so that we can feed it into our machine learning model. So if we think of this interface, you can see that there are other layers indicated on the left side, and you can pretty much click and drag these layers. It's almost like playing with Lego blocks, and it's a more interactive way to build your neural networks. Struggling to get that connection. Okay, there we go. So that was just to demonstrate. And then once you've built your network, typically you want to see if the network makes sense before you start training it. So you can quickly do an analysis of it. So the analysis is just going to look at, are there any errors or warnings associated with this model that you have designed, right? And in this case, it's telling me that there's one error. I'm assuming because I have a random layer lying around somewhere, but the AlexNet is a perfect network. It's been tried and tested. But once you're happy with your model and it's performing as you expected, you can simply export it, or you can generate the code for creating that model. So the value of having this is some people don't enjoy programming, and that's okay because there's an interactive way to generate your code. Or maybe you just want to explore many different things without investing too much effort or time from your side. So this is why this is quite helpful. And we can see that it's all very well documented and easy to follow. So the next thing we want to do is we want to access and explore our data. So I'm just going to open the folder within which our data is stored. And we see here that we have 100 training images. So this means we have 100 good bolts. None of them have any defects or faults. Right? And the next thing we want to do is make sure that MATLAB has access to that data. And we do this by using the function image data store. So the image data store would point to the repository within which that data is stored. So it doesn't actually pull it into memory. And this means you can work with arbitrarily large amounts of data at a time. And in this case, we've identified that there's 100 images in that folder. The next thing we want to do is to extract our 7th fully connected layer. Right? And we'll use it to extract those training features that we want to feed into our machine learning model. So here we've created our variable training features, and we can see a matrix of information. And here I'm just going to visualize what those features look like. So you'll see that this is similar to what we spoke about in the presentation, where you can see that there's very strong edge detections happening in some regions. Some of the filters would be extracting things like color and texture, for example. Then once we have our data, well, extracted the features from our data, we want to train our support vector machine. So we will use this fit classifier model function where we are fitting an SVM model. So we just train it. Essentially, we just pass in our training features as well as our labels. So the label is just saying all these images that we're looking at are the same and they're all good. So they have no defects. So now that we have trained our model, we want to want to test it on our testing set. Again, I'm just going to open it up. And we can see we had 4 defective bolts and 96 good bolts. So that's our testing set. Right? And again, we want to make sure MATLAB has access to it so that we can test it. And in order to perform the testing, we'll use the predict function. And we're passing in the model that we trained along with the testing features that we have extracted. And we get a score. And in this line, I've just ordered the score in ascending order, so from lowest to highest. And what the score is telling us is that it's giving us information about the similarity between our testing image and the rest of the training set. So if the score value is really low, it implies that there's very little similarity between the testing image and the training set, and that indicates an anomaly. And in cases where the value is high, it means they're strongly similar, and therefore there's no anomaly that's been detected. Okay. So I'm just going to display these results. So I'm going to display an array, a matrix or montage of our images, and they'll be arranged according to the score they were assigned by our model. And what I've done here is I've simply highlighted the bolts that we know for a fact are faulty with these yellow blocks. And so we see that somehow the machine learning model identified these 4 bolts as being more defective than this one over here. And this can't be right because we know that these bolts are good. So we performed some investigation to find out why that's happening. And we found that by taking a normal bolt, so one without any defects, and simply flipping the image, the score would drop significantly. And this means that the position and the orientation of our bolt in the image gave some sort of information to the machine learning model about whether it's a good bolt or a bad bolt. And we don't want that to happen. And this is why pre-processing is such an important step in everything that we do. So the next thing we'll want to do is to make sure to align our bolts so that they're positioned in the identical fashion and they're oriented accordingly. So for example, we will look at these two. They're positioned and oriented slightly differently. So we will try and register these images, meaning to just align them. And to do this, we'll use the registration estimator app, which again, you can find in your apps tab. So the first thing we'll do is to load in our images from our workspace. So the first thing we'll load in is our reference image. So this is the reference image around which we will start to move the other images so that they're aligned with it. And then we identify which image is the one that will be moving. Then we can start. And at this point, it's just telling me it's much easier to align images if they're in grayscale. So it's simply doing that conversion for us. And we can see when we place them on top of each other that they're not aligned at all. So we want to align them. And here we've been given ideas about the different registration techniques that are available. So I'm not an expert at image processing. So all I did was I played around with the different things that are available here and then hoped for the best, right? And I discovered that the intensity-based registration worked the best. So I selected that. And I played around with some of these parameters and I discovered that, okay, the affine transformation is what I needed. Then when I registered the images, it registered them perfectly. So I was really happy with that. And then I just did a flicker looking at it in different ways to see that it is aligned well, right? Then once you're happy with that, you can again export the function or generate the function. And again, you can see that it's very well documented. And the process that this function follows is essentially the same to what we did in the app, all the way from importing our images to getting that alignment at the end. Right. So now let's just use that function because I've already saved it from previous runs. And then the next thing we want to do is to create a mask, right? Because if we feed something that looks like this into our model, it will start to interpret these as features to be learned. And that's not what we want. So we'll create a mask. And we can apply this mask to all the images because they're all positioned and orientated in the exact same way. So we apply it to our images, and this is what it would look like. So what we've done here is we've minimized the amount of information that our model has to learn. And the background is unnecessary information, and it's just causing confusion to our model. Then once we've done that, we can develop our predictive model. So in this section, it's essentially everything that we've done from start to end, except now we're using our pre-processed image data. Right. And we can see a significant improvement in the results, where now the bolts that we were certain were defective appear in our first row of information and in the first 4 columns as we expected it. And now we can look at the results side by side to see that improvement. Looking at them, we can see that these 4 have now been shifted out, and it has identified that this one is in fact more effective than the others. So then once you've developed your algorithm, you probably want to deploy it and integrate it into your other systems. So because of time, I will not go through this today, but I will, as part of the source code that you'll receive, I have indicated an area where you can see how you can deploy the same algorithm onto a Raspberry Pi. Right. So if, let's say, you took your model and you tested it on additional images and you discovered that it's still not performing as well as you would have hoped. So there's a series of things you can still try to enhance its performance. So the first is you could do some image augmentation. So this means applying a series of transformations. So some rotations, reflections, some cost adjustments to kind of create the illusion of having a larger data set to your algorithm. Or you can increase the number of images, so you could just take more pictures, right? Or you can do some appropriate pre-processing on the images. We saw in the demo that just changing getting rid of the background information improved the results quite significantly. And you can fine-tune the hyperparameters of the classifier, right? So to tune a little bit more so that it's more suited for application. And if all else fails, perhaps just use a completely different pre-trained network, because they all have a different collection and number of filters that are available. And as I mentioned before, Nuts and Bolts is a very real company, and we had to start thinking about how are we going to get them access to this types of technology. So on the left-hand side, we have deployed the pre-processing as well as the model and the post-processing onto a Xilinx board. And on the right-hand side, we did the same, but deploying to a Jetson Xavier. And all of this was achieved without having to redo the work. It's literally just a series of click and drags and things like that. So just to elaborate a little bit further on the deployment support, so MATLAB enables you to deploy your deep learning models to various embedded hardware platforms. So things like your ARM or Intel CPUs, your NVIDIA GPUs and Intel SoCs, as well as your FPGAs and your Xilinx board. So you can pretty much explore and target embedded hardware very easily. MATLAB can also deploy to desktop or server environments. So if let me just take out my pointer again. So if we look here, you could deploy it as a cell phone application. Perhaps the person on the site can just take a picture of the bolt, and that can go through the processing, which might be a lot easier in that case. Or perhaps you want to make it accessible to the entire enterprise or to run in more real-time applications. So you can scale it to platforms like your AWSs or Azure. So just some key takeaways. MATLAB provides a very flexible and powerful environment for getting started with your computer vision workflows. And it provides an extensive framework that can cater for your technical workflows. So all the way from your data accessing all the way through to deployment. So I hope you enjoyed this webinar and that it has been valuable to you within the context of your work. Please reach out to me. I'd love to speak to you more about your work and how we can tailor what we have here to your specific applications. So I hope we'll see you at the next webinars, and please complete the survey. And we're always curious to see how we can improve how we do things. And once you've completed the survey, you'll receive all the source code and accompanying material that has been used today. So for now, that brings us to the end, but please ask questions. I see Fiona has a question.
Hi, morning.
Morning.
So I have a question. Is there a minimum resolution that the images have to be for the algorithm to work? And then also, have you ever considered what happens when two images are of different resolutions? How would that affect how the algorithm works? Thanks.
Awesome. So the level of resolution would be dependent on your specific application. So for example, if we think maybe you're processing satellite images, so not necessarily in the context of this anomaly detection work in this kind of format, if you're looking at satellite images, you might require much higher resolution. So it really depends on the complexity of your product and what it is you're trying to detect from that product. I'm sorry, Fiona, what was your other question?
My other question was, what would possibly happen if you had a set of images and then some of them are different resolutions? Would it pick it up as a defect or?
Oh, no. So that would then form part of the pre-processing stage of what you're trying to do. So in MATLAB, you can resize your images so that they're all at the same resolution, because you wouldn't want it to pick up that as a feature, for example.
Okay, thank you.
Thanks.
Thanks, Demi. Any other questions from the floor? Feel free to type it out in the chat as well.
Hello.
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 Hi, man. How are you?
Yeah, fine, ma'am. Actually, ma'am, to train the deep neural network, let us we are actually how many images we need, a minimum number of images. Let us, I think, if I got, let us 2 lakhs, 3 lakhs images to train the deep neural network, it is possible to store these images in CPU. It is not possible. So where I can store the images so that I can train my deep neural network.
So are you asking where can you store your images?
Exactly.
Yes. All right. So MATLAB integrates with other platforms or databases. So you can pretty much store it wherever it is stored currently. It doesn't have to be on your local machine. It can be on some cloud somewhere. And then we would just pull that information from there, or perhaps deploy the model to that platform so that it can train and run from there.
If I am having my own data set, so when I can store these data, these images, let us 2 to 3 lakhs images I am having own.
Sorry, please repeat that. I couldn't hear you very
Actually,
clearly.
I am having my own data set, and the data set having maybe 3 lakhs images. So where I put these images to train my deep neural. So let us I'm going for designing a deep neural network from scratch. So I want to train this network. I am having
you want to
own
train
data.
it from scratch.
Yeah. I'm having 3 lakhs images. So where I store these data so that I can assess, I can train my deep neural network.
How much data do you have?
Yes.
So how much data
Maybe
you have?
3 lakhs images.
3 lakhs images.
Yeah.
I'm not familiar with that.
Okay. So is that a storage issue that you're worried about? Not being able to store it locally?
Yeah.
Yeah. So you can put it on a server, for example, and you can access it from a server locally as well.
Yeah. Okay. Thank you.
So just to get, the juices flowing, I'm just going to go through some frequently asked questions, right? Sorry, I'm going the wrong direction. All right, so the first being, is Nuts and Bolts Manufacturers a real company? No, it is not. I really just wanted to communicate the vision of this workflow, and I hope that came across. You had text in your MATLAB script. How did you do that? So I don't know if you guys are familiar with the MATLAB live scripts, but it's essentially a different way of writing, editing, and running MATLAB code, which allows you to kind of build this interactive narrative where you can include titles and descriptions and images. And it's usually very useful for documentation purposes. And can I use deep learning models developed in other platforms in MATLAB? Yes, you can. So MATLAB is part of the Open Neural Network Exchange. So that means you can import models that you've built perhaps in PyTorch or TensorFlow or these various platforms that are available right now, and you can modify them within the MATLAB platform. And my model takes a long time to train. How can I make it train faster? So in this case, MATLAB allows you to parallelize the training. So you can perhaps run it on your cores on your machine or to some cloud environment like your Azure to run it in parallel. And is there a quick MATLAB tutorial on the concept we've covered today? Yes, there are. So we have the MATLAB on-ramps, and with MATLAB, image processing, machine learning, and deep learning. And all these on-ramps are free, and they take about 2 hours to complete, and you get a certificate at the end of it, which is really great. So yeah.
There's just a question in the chat, if you can pick that up for tomorrow.
Okay. What would the reaction time be for a typical system like this? Is it something that you can use on the floor, or would you need to isolate the components and wait for processing? It depends. It depends on what workflow you would want for yourself. So again, we can deploy it to some edge device where it can be used directly on the floor, or it could be that the data gets stored on the cloud, and then it can be pulled by a different group of people on the other side so they can process it.
Yeah, just to add to that as well, it depends on the type of neural network you're using. Like I mentioned in the chat there, the AlexNet is particularly good for real-time applications. It might not be the most accurate, but it's fast. And you can play around with the type of network you use to get that speed that you want to be able to use it on a floor. I hope that answers your question. All right, any other questions from the floor?
Right, perfect. Thank you guys so much for joining. Feel free to message us if you need anything. Perfect.
Yeah, we'll stick around if anyone wants to ask more questions. So, Dumisani, to answer your question there, we don't have specific master's or PhD research topics out of our company, but it's an interesting idea. It's something I could potentially take up to the relevant people in the company.